Here we're told that 80% of the energy from a 40-watt fluorescent light tube, so here's a fluorescent light tube, is radiated as heat. The surface temperature of the bulb is 50 degrees C. Calculate the rate of entropy production for this light bulb. So to do this, we're going to make use of the entropy equation. Since we're trying to find the rate of entropy production, my first thought is to use the entropy equation because that involves entropy production. So let me write it down like this. Let me write the whole thing and then I'll discuss it. So here is the entropy equation. I'm going to apply it to a control volume that surrounds the light bulb. So there's some heat that's coming in. I'll just Q dot in. Actually, the heat's going out, so it'll be negative. And then there's also some power that's going into it. Let's call it W dot. That's electrical power that's going in. So we're told that 80% of the energy that's going in to that 40-watt bulb is going out as heat. So we know that Q dot into is going to be a negative 0.8 times 40 watts, right? So that comes out to be 32 watts. So there's actually 32 watts of heat transfer out of the control volume. The temperature at the bulb surface is where that heat is being is escaping or crossing the boundary is 50 degrees C, but let's go ahead and add in the 273 to make it Kelvin, because in our entropy equation this temperature here is an absolute temperature, so we need to make it Kelvin. Right, so we do that, that comes out to be what? 323 Kelvin. So what I'm doing is I'm just kind of filling in some of the terms in this entropy equation. This is the time rate of change of entropy within the control volume. We're going to say that that's 0. We're going to assume that we're dealing with a steady state. There's no mass flowing into or out of that control volume. There's only energy exchanges, so there's no mass going in or out. So these are both 0. And so what we're left with from the entropy equation, the sigma dot is the integral of the heat transfer in divided by the absolute temperature where that heat transfer is occurring all over the entire boundary. Okay, so we can just go ahead and substitute in. So and there should be a negative sign here because when I bring one of these to the left-hand side, it gives me a negative sign. So this just ends up becoming Q dot out all over T. So this will just end up being, there's a negative sign there. So this will be 32 watts all over 323 Kelvin. And when you plug those numbers in, you'll get the rate of entropy production is 0.990 watts per Kelvin. There's another 0 in there, sorry. Watts per Kelvin. So that's the rate of entropy production. Since it's not 0, clearly that means that this is an irreversible process here. So there's some irreversibility in that light bulb. Okay, that's all there is to it. We're going to go ahead and end the example there.